Hey there, science fans. Today we're diving into the fascinating world of computer science, specifically sorting algorithms. You know, those clever methods computers use to organize data? We'll be exploring Bubble Sort, a simple yet insightful algorithm. Now, you might be wondering, why should we care about sorting? Well, imagine looking for your favorite book in a library where the books are randomly placed. Chaos. Sorting algorithms help us arrange data in a meaningful order, making it easier to search, analyze, and understand. Bubble Sort is like organizing a shelf of toys by size. We compare adjacent items and swap them if they're in the wrong order. We repeat this process, gradually bubbling the largest items to their correct positions. Intrigued? Let's unravel the magic of Bubble Sort. Imagine you're at a toy store and there's a shelf with 5 toy cars arranged in a jumbled mess. The cars have numbers on them, 4, 2, 5, 1, and 3. We want to arrange these cars in ascending order from the smallest number to the largest. This is where Bubble Sort comes in handy. Just like we compare and swap the cars on the shelf, Bubble Sort compares and swaps adjacent elements in a list until the entire list is sorted. Ready to see Bubble Sort in action? Let's go! Remember our toy cars? Let's see how Bubble Sort would sort them. First pass 1, we compare the first 2 cars, 4 and 2. Since 4 is greater than 2, we swap them. Now the order is 2, 4, 5, 1, 3, 2. Next, we compare the second and third cars, 4 and 5. They're in the correct order, so we move on. 3, we compare the third and fourth cars, 5 and 1. 5 is greater than 1, so we swap them. The order is now 2, 4, 1, 5, 3, 4. Finally, we compare the fourth and fifth cars, 5 and 3. We swap them because 5 is greater than 3. The order after the first pass is 2, 4, 1, 3, 5. Notice that the largest number, 5, has bubbled to its correct position at the end of the list. Second pass. We repeat the process, comparing and swapping adjacent elements. After the second pass, the second largest number, 4, will be in its correct position. We continue these passes until the entire list is sorted. Let's see how we can implement Bubble Sort in Python. Python def Bubble Sort R. An equal sign length R for I in range, and for J in range, 0 ni1. If arg rj plus 1, arg rj plus 1 equals sign rj plus 1, arg return r hash example usage numbers equals sign 42513, sorted underscore numbers equals sign bubble sort numbers, print sorted numbers, hash output 1, 2, 3, 4, 5. This code defines a function called that takes a list as input and returns the sorted list. Section 5, understanding the code line by line. Let's break down the code step by step. 1. This line defines the function that takes one argument, the list we want to sort. 2. We store the length of the list in the variable. 3. This outer loop iterates through the list times, ensuring we perform enough passes to sort all elements. 4. The inner loop compares and swaps adjacent elements. Notice that with each pass of the outer loop, the inner loop iterates one fewer time. This is because the largest elements are already in their correct positions at the end of the list. 5. This line compares 2 adjacent elements. If the element at index is greater than the element at index, we need to swap them. 6. This line swaps the elements using a neat Python trick. 7. After all the passes, the function returns the sorted list. Section 6. How fast is Bubble Sort? We've seen how Bubble Sort works, but how efficient is it? In other words, how does its performance change as the number of elements in the list grows? The efficiency of an algorithm is often described using its time complexity. Time complexity tells us how the execution time of an algorithm increases with the input size. For Bubble Sort, the worst-case scenario is when the list is initially in reverse sorted order. In this case, Bubble Sort needs to perform the maximum number of comparisons and swaps. Section 7. Time complexity and recurrence relations. We can express the time complexity of Bubble Sort using a recurrence relation. Don't worry, it's not as complicated as it sounds. For a list of elements, Bubble Sort makes comparisons in the first pass, comparisons in the second pass, and so on. The total number of comparisons can be represented by the sum. This sum simplifies to therefore the time complexity of bubble sort is said to be on the order of written as O(n)² squared. This means that the execution time increases quadratically with the input size. Section 8. Beyond bubble. Sort, when to use and when to choose alternatives. While bubble sort is easy to understand and implement, its O(n)² time complexity makes it inefficient for large datasets. For smaller datasets, bubble sort can be a good choice due to its simplicity. However, for large datasets, more efficient sorting algorithms like merge sort or quick sort are preferred. The choice of sorting algorithm depends on factors like the size of the dataset, the initial order of the data, and the programming language being used. Section 9, conclusion. Bubble sort in a nutshell. Congratulations! You've journeyed into the world of sorting algorithms and learned about bubble sort. We've seen how it works, how to code it, and how to analyze its time complexity. Remember, bubble sort is like organizing your toys. Compare adjacent items and swap them if they're in the wrong order. Repeat until everything is in its right place. While bubble sort might not be the fastest sorting algorithm out there, it's a great starting point for understanding the fundamental concepts of sorting. So keep experimenting, keep learning, and keep the spirit of scientific curiosity alive.